In the summer of 2022, the James Webb Space Telescope sent its first images back to Earth. They were extraordinary, not in the way that press releases use that word, not extraordinary as a polite compliment to a successful engineering project. Extraordinary in the literal sense, beyond ordinary, outside the range of what the models predicted, showing things that the best scientific understanding of the universe said should not be visible at those distances, in those numbers, with those characteristics. The scientific community's response was measured in public and considerably less measured in private. Papers were published, conferences were convened, theoretical frameworks were examined and, in some cases, quietly set aside, because James Webb was not finding what it was expected to find. It was finding more, earlier, larger, brighter, more organized, more chemically complex, more structurally advanced, at distances and at times in the universe's history when none of those things were supposed to be possible. Not by a small margin, not by an amount that could be explained by measurement uncertainty or instrumental calibration issues, by margins that required serious people to say, in careful scientific language, that something is wrong with our understanding of how the early universe assembled itself. Something was wrong, not with the telescope. The telescope was performing beyond specifications. It was seeing further and more clearly than anyone had dared hope. Something was wrong with the map we had built of how the universe works, how galaxies form, how they grow, how long these processes take, what the universe should look like at different points in its 13.8 billion year history. That map was not matching the territory. And the further Webb looked, the more the mismatch grew. This is the story of what James Webb found, not the sanitized version in the press releases, not the carefully worded scientific language that softens the implications. The full version, what the telescope actually saw, what it means for the models, what it means for our understanding of how everything came to be, and why, nearly 4 years after those first images arrived, the scientists who study them are still arguing about what to do with what they show. Before we can understand what James Webb found, we need to understand what it was looking for, what the models predicted it would see, what the universe was supposed to look like at those distances and those times. The standard model of cosmology, the framework that has been refined and tested over half a century of increasingly precise observations, describes the universe's history in terms of epochs. The Big Bang at time zero, a period of inflation in the first fractions of a second, a radiation-dominated era, matter beginning to dominate, recombination at 380,000 years, when the first atoms formed and the universe became transparent to light. The cosmic dark ages. The cosmic dark ages are perhaps the most evocatively named period in the universe's history. After recombination, the universe was dark. Not dark in the way a room is dark when the lights are off. There was still some residual radiation. Dark in the sense that there were no stars yet, no galaxies, just hydrogen and helium gas, slowly cooling, slowly clumping under the influence of dark matter, slowly assembling the seeds of what would become the first structures. This period lasted for roughly 100 to 200 million years. In cosmological time, not very long, but long enough, according to the standard model, that the transition from featureless gas to organized galaxies was expected to be gradual. The first galaxies were predicted to be small, primitive, poorly organized, containing relatively few stars, chemically simple, mostly hydrogen and helium, with little of the heavier elements that stellar nucleosynthesis produces over time. The universe at 400 to 500 million years after the Big Bang, the standard model predicted, should look like a construction site. Foundations being poured, structure being assembled, everything small, young, and messy. James Webb was designed to see into that construction site, to observe those first galaxies and confirm that the standard model was correct about what the early universe looked like. Confirmed no such thing. What it found instead was, in some cases, more like a finished building than a construction site. Galaxies that were massive, organized, and in some cases extraordinarily bright at times when the standard model said they should barely exist. The construction site was already occupied, and the residents were not supposed to be there yet. Let's start with the first major finding that set the scientific community on edge. In July 2022, within weeks of Webb's first science observations becoming available, a team of astronomers identified a set of candidate galaxies at extremely high redshift. Redshift is the cosmological equivalent of a Doppler shift. As the universe expands, the light from distant galaxies is stretched to longer, redder wavelengths. The higher the redshift, the further away the galaxy, and the further back in time we are looking. These candidate galaxies had redshifts suggesting they existed when the universe was between 300 and 500 million years old. Not unusual for Webb, detecting galaxies at these distances was exactly what the telescope was designed to do. What was unusual was their brightness. Galaxies at these redshifts, according to the standard model, should be faint. They are small, young, and contain relatively few stars. The further back you look, the younger the universe you observe, the fainter the typical galaxy should be. These galaxies were not faint. Some of them were remarkably bright for their distance. Brighter than the models predicted by significant factors. Not a small calibration adjustment, but a substantial discrepancy. When astronomers calculated how many stars these galaxies would need to contain to produce the observed brightness, the numbers came out far larger than the models said should be possible at those times. These were not small, young, primitive galaxies. Some of them appeared to already contain billions of stars. Some of them appeared to have stellar populations comparable to galaxies in the much later universe. Galaxies that had had billions of years to grow, not hundreds of millions. The paper describing these findings, published in the journal Nature in late 2022 and led by Evo Lab of Swinburne University, described the results plainly. If these galaxies were real, if the distances and brightness measurements were correct, they would challenge the standard model of galaxy formation in significant ways. The reaction from the scientific community was immediate and divided. Some researchers argued that the galaxies could not be as distant as they appeared, that the photometric redshift estimates used in the initial analysis were uncertain enough that the galaxies might be much closer, and therefore much smaller and less massive than they appeared. Others argued that the brightness might be partly produced by active galactic nuclei, supermassive black holes at the centers of the galaxies, accreting material and radiating energy. Black holes can produce enormous luminosity without requiring correspondingly enormous stellar masses. Both explanations were reasonable. Both could potentially explain the observations without requiring fundamental revisions to the standard model. But then the spectroscopic confirmations began arriving. Spectroscopy, the technique of spreading a galaxy's light into its component wavelengths and reading the absorption and emission lines that reveal its distance, temperature, chemistry, and dynamics, is far more reliable than photometric redshift estimates. When Webb began obtaining spectra of the candidate massive early galaxies, the results were not reassuring for those hoping for simple explanations. The distances were confirmed. These galaxies were real, and they were where the photometry said they were. The standard models problem did not go away. It got worse. Let's talk about a specific galaxy that has become something of a symbol for everything James Webb has found that doesn't fit. Its catalog designation is Jwst Z14-0. It was identified in the Jade survey, the James Webb Advanced Deep Extragalactic Survey, and confirmed spectroscopically in 2024. Its redshift is 14.32. This means we are seeing it as it existed when the universe was approximately 290 million years old, less than 300 million years after the Big Bang. 300 million years sounds like a long time, and by human standards it is incomprehensible. But by the standards of galaxy formation, 300 million years is almost nothing. It is the blink of an eye in a universe that has been assembling structure for nearly 14 billion years. In 300 million years, according to the standard model, you can form small galaxies. You can build up some stellar populations. You can begin the process that will eventually create the massive galaxies of the later universe. What you are not supposed to be able to do is produce a galaxy with the properties of Jwst Z14-0. This galaxy contains an estimated 500 million solar masses of stars, 500 million suns, assembled in less than 300 million years. The standard model simulations, run with the best computational resources available, struggle to produce galaxies this massive this early without invoking processes that have not been observed. But the mass is not the most striking thing. Jwst Z14-0 contains oxygen. Heavy elements, anything heavier than helium, are produced by stellar nucleosynthesis. They are made inside stars through the fusion reactions that power those stars, and they are released into the surrounding gas when those stars die through stellar winds and supernova explosions. This process takes time. You need multiple generations of stars to build up significant abundances of heavy elements. Finding oxygen in a galaxy 290 million years old means that at least one, and probably several generations of stars had already lived, burned through their fuel, and died, all in less than 300 million years. The stars that produced the oxygen in Jwst Z14-0 were born, lived their entire lives, and exploded before the universe was 300 million years old. This is not impossible. Massive stars can live and die in a few million years. If the first generation of stars in this galaxy were extremely massive, the kind of massive stars that the early universe may have preferentially produced, before the interstellar medium had been enriched with the heavy elements that allow lower mass stars to form, then multiple stellar generations in a few hundred million years is at least conceivable. But conceivable and expected are different things. The standard model did not predict galaxies like Jwst Z14-0 at this redshift, with this mass, with this level of chemical enrichment. It is a data point that requires explanation, and so far, no fully satisfying explanation has been provided. Let's step back and understand why the mass problem is so difficult. Galaxy formation in the standard model is not a random process. It is governed by the availability of dark matter halos, the gravitational scaffolding within which ordinary matter collects and forms stars. Dark matter clumps first under gravity, forming halos of increasing mass. Ordinary matter falls into those halos, cools, and forms galaxies. The mass of the galaxy is constrained by the mass of the dark matter halo. The mass of the dark matter halo available at any given time is constrained by how long the universe has had to grow halos through gravitational collapse. And the growth of dark matter halos follows a specific mathematical distribution, the halo mass function, that the standard model predicts with considerable precision. At 300 million years after the Big Bang, the standard model predicts that halos massive enough to host the galaxy's web is finding should be extremely rare. Not impossible, the tail of the distribution extends to high masses even in the early universe. But rare enough that finding multiple such galaxies in a relatively small survey area would be statistically surprising. And Webb is finding them. Not one or two. Population. More massive early galaxies than the statistical distribution of early dark matter halos would predict. Either the halo mass function is wrong, meaning our understanding of how dark matter assembles in the early universe needs revision, or the efficiency with which ordinary matter converts to stars in the early universe was much higher than the models assume. Or both, or something else entirely is happening that the models do not capture. Each of these alternatives has implications for other aspects of the standard model. Changing one thing changes other things. The model is a system, and pulling on one part of it pulls on all the connected parts. This is why the massive early galaxy problem is not a minor anomaly to be corrected with a small parameter adjustment. It potentially requires a rethinking of how star formation worked in the early universe, how efficiently dark matter assembled into halos, and possibly whether the initial conditions of the universe are exactly what we thought they were. Now let's talk about another Webb finding that sits uncomfortably alongside the massive galaxy problem. The early universe should be chemically simple. This is not an assumption. It is a direct consequence of Big Bang nucleosynthesis, the process by which the first elements were formed in the first minutes after the Big Bang. In those first minutes, the universe was hot enough and dense enough for nuclear fusion to occur, producing hydrogen, helium, and tiny amounts of lithium. Nothing heavier. The heavy elements, carbon, oxygen, nitrogen, iron, the elements of life and planets, all came later from stars. At early times in the universe's history, the interstellar medium, the gas between stars, should be almost entirely hydrogen and helium. The first stars form from this pristine gas. When they die, they enrich the surrounding medium with heavier elements. But the enrichment is gradual, and the first generations of galaxies should be dominated by very metal-poor stars, stars with very low abundances of elements heavier than helium. In astronomy, everything heavier than helium is called a metal. Metal-poor means low in carbon, oxygen, nitrogen, iron, everything that stars produce. The early universe should be very metal-poor. And yet Webb keeps finding evidence of chemical enrichment in the early universe that the models do not predict at those times. Jade's Jwst Z14-0, as we discussed, contains oxygen at a time when it should barely have had time to produce any. But it is not alone. A galaxy designated GN-Z11, first identified by Hubble but studied in far more detail by Webb, sits at a redshift of about 10.6, corresponding to about 430 million years after the Big Bang. Webb's spectroscopic observations of this galaxy revealed nitrogen emission lines at a strength that implies a nitrogen abundance far higher than expected for a galaxy this young. The nitrogen discovery was particularly startling because nitrogen is produced by a specific type of stellar process, primarily in asymptotic giant branch stars, a late evolutionary stage that lower mass stars go through. These stars are relatively long-lived compared to the massive stars that produce oxygen. For nitrogen to be enriched to the levels Webb detected in GN-Z11, a sophisticated stellar population with multiple generations of different stellar masses would need to have lived and died in less than 430 million years. This is not easily explained. The leading hypothesis for GN-Z11's chemical enrichment involves either a globular cluster, an extraordinarily dense collection of stars that could have produced multiple stellar generations very quickly, or a population of extremely massive, short-lived stars called Wolf-Rayet stars that produce nitrogen through their powerful stellar winds. Neither explanation is fully satisfying to all researchers. Both require conditions in the early universe that the standard models did not specifically predict. Both imply that star formation in the early universe operated in ways that are different from star formation in the later universe. Faster, more efficient, more concentrated, producing more extreme objects, which is itself a significant finding. If the physics of star formation in the early universe is meaningfully different from what it is today, then the models built on observations of nearby galaxies may not apply to the conditions of 400 million years after the Big Bang. The early universe may have had its own rules. Now let's talk about what might be happening in the very centers of these early galaxies. Because some of the most surprising Webb findings involve not the galaxies themselves, but what is growing at their hearts. Supermassive black holes, the enormously massive black holes that sit at the centers of most large galaxies, including our own Milky Way, are expected to grow gradually over time. They begin as smaller black holes, the remnants of the first massive stars or the products of other early formation mechanisms, and they grow by accreting gas and by merging with other black holes over billions of years. The relationship between a galaxy and its central black hole is remarkably consistent in the nearby universe. The mass of the central black hole is typically about 0.1 to 0.5% of the mass of the galaxy's central bulge. This relationship, called the black hole mass to bulge mass relation, is so consistent that it appears to reflect a fundamental connection between the growth of galaxies and the growth of their central black holes. They seem to have co-evolved, growing together in a way that maintains this consistent ratio. At early times in the universe's history, this coevolution was expected to produce black holes that were proportionally small. Young galaxies should have proportionally small black holes, because both are growing from seeds. Webb is not finding proportionally small black holes. In galaxy after galaxy in the early universe, Webb's spectroscopic observations are finding signatures of active galactic nuclei, accreting supermassive black holes producing enormous amounts of radiation that are far more massive relative to their host galaxies than the nearby universe relationship predicts. A galaxy 400 million years old with a stellar mass of 100 million suns should have a central black hole of perhaps 50,000 to 500,000 solar masses, according to the local relationship. Webb is finding black holes of tens of millions of solar masses in galaxies at these ages. Not proportionally small, proportionally enormous. Black holes that are 100 or 1,000 times more massive than the local relationship predicts for galaxies of their size. This is called the overmassive black hole problem, and it is one of the more significant puzzles Webb has delivered. If the black holes at the centers of early galaxies are far more massive than their host galaxies would predict, then either the black holes grew first before the galaxies caught up, or the black holes grew faster than the galaxies, or the seeding mechanism for early supermassive black holes was different from what models assume. One intriguing possibility is that the earliest supermassive black holes formed not from the remnants of massive stars, but directly from the collapse of enormous gas clouds, direct collapse black holes, sometimes called direct collapse black hole seeds. Under the right conditions in the early universe, before significant stellar feedback had disrupted the gas in these regions, a massive gas cloud could collapse directly into a black hole without forming stars first, producing a black hole seed that is immediately far more massive than anything a stellar remnant could provide. This mechanism has been theorized for years. Webb has not directly confirmed it, but the overmassive black holes Webb is finding in early galaxies are consistent with this mechanism and inconsistent with the simpler seed models that had been favored. Let's talk about a discovery that went largely unnoticed outside the scientific community, but that carries implications as significant as the massive galaxy problem. In the first major data releases from the Jwst survey, astronomers found something unexpected in the morphology, the shapes of early galaxies. Galaxies in the nearby universe come in a variety of shapes. Spiral galaxies, like the Milky Way, have organized, rotating disks with spiral arms. Elliptical galaxies are smooth, round, or elongated blobs, dominated by old stars on disordered orbits. Irregular galaxies have no organized structure. In the nearby universe, spiral disk galaxies and elliptical galaxies roughly balance each other in terms of numbers among the most massive galaxies. The disk galaxies are generally younger, still forming stars actively. The ellipticals are generally older, having used up their gas. In the early universe, the standard model predicts that well-organized disk galaxies should be rare. Disks form through the slow, ordered accumulation of gas in rotating halos, a process that takes time and requires conditions to be stable enough to allow the orderly rotation to establish itself. Early galaxies, forming quickly from dense, turbulent gas in an environment with frequent mergers, were expected to be predominantly irregular, chaotic, lumpy, asymmetric. Webb is finding disks, not everywhere, not exclusively, but in numbers and at redshifts that the standard models did not predict. Galaxies with well-organized, rotating disk structures at redshifts of 4, 5, 6, 7, corresponding to times when the universe was between 600 million and 1 billion years old, are appearing in Webb surveys in larger numbers than the simulations produce. The Cosmic Evolution Early Release Science Survey, one of the major Webb survey programs, reported in 2023 that well-organized disk galaxies were significantly more common in the early universe than predicted by leading cosmological simulations. Not by a small factor, by a factor of several. This matters because disk formation is sensitive to the conditions of galaxy formation in ways that more spherical or irregular morphologies are not. A disk requires sustained, ordered infall of gas. It requires a relative absence of major mergers that would disrupt the structure. It requires stability. If disks are common early, something about the early universe was providing more stable, more ordered conditions for galaxy formation than the models assumed. Or the models are wrong about how susceptible disks are to disruption by mergers. Or something else entirely, perhaps some physical process that the models do not include is helping to organize early galaxies into disks faster than expected. The morphology finding is one of the more puzzling Webb results precisely because it is not obviously explained by any single modification to the standard model. It is a structural finding about the shapes of things, and shapes are sensitive to the detailed dynamics of formation in ways that mass and brightness are not. Here is a finding that emerged not from a single paper but from the accumulation of results across multiple Webb programs over the first 3 years of science operations. The universe's early star formation history is more compressed than expected. The Standard Model predicts a specific history for when most of the universe's stars were formed. This history is called the cosmic star formation rate density, the total mass of stars being formed per year, per unit volume of the universe as a function of time. It rises from essentially zero at the earliest times, peaks somewhere around 2 to 3 billion years after the Big Bang, and then declines as gas is consumed and star formation quenches. Webb is finding evidence that the early rise of this curve is steeper than expected. Star formation in the universe was ramping up more rapidly in the first billion years than the models predicted. The rate of star formation in early galaxies was higher, and it began earlier than the standard framework anticipated. This finding is not in a single paper. It emerges from the aggregate of Webb observations across multiple surveys, multiple galaxy samples, and multiple research teams. It is a statistical finding, not any single galaxy doing something impossible, but the population of early galaxies collectively showing higher star formation rates than predicted. What causes more rapid early star formation? Several possibilities have been proposed. One is that the dark matter halos in the early universe were more concentrated than standard models predict, providing deeper gravitational wells that allowed gas to compress more efficiently and form stars faster. Another is that the physics of gas cooling in the early universe, the processes by which gas loses energy and compresses into the dense clouds where stars form, was more efficient than assumed, perhaps because the gas was less enriched with heavy elements and therefore behaved differently than the cooler, enriched gas of later epochs. A third possibility involves the role of cosmic rays and magnetic fields in suppressing star formation in nearby galaxies, processes that may have been less important in the early universe, allowing star formation to proceed at higher efficiency than it does today. None of these explanations have been definitively confirmed. All of them are being modeled. All of them represent modifications to the standard picture of how the early universe worked. And all of them together contribute to the growing sense in the cosmological community that the early universe was a more active, more efficient, more rapidly evolving place than the standard model captured. Let's talk about quenching, because this is where the Webb findings become most difficult to explain. Quenching is the process by which star formation in a galaxy stops. A galaxy that is actively forming stars is called a star-forming galaxy. A galaxy that has stopped forming stars, that has used up or expelled its gas supply, is called a quenched galaxy or a passive galaxy. In the nearby universe, quenched galaxies are common. Most of the most massive elliptical galaxies are quenched. They formed their stars billions of years ago and have been passively cooling ever since. The processes that quench galaxies are reasonably well understood. Feedback from active galactic nuclei can heat and expel gas, preventing further star formation. Ram pressure stripping in galaxy clusters can remove gas. Simple exhaustion of the gas supply over billions of years of star formation can end the process. What is not well understood is how quickly quenching can occur. In the standard model, the most rapidly quenching galaxies would take hundreds of millions to a billion years to shut down their star formation after whatever triggering event initiates the process. Quenching is not expected to be instantaneous. Webb is finding quenched galaxies in the early universe that appear to have shut down star formation far faster than the models predict. A galaxy designated Jwst Z7-01 was found in 2024 to be a quenched galaxy at a redshift corresponding to when the universe was about 700 million years old. This galaxy had formed stars rapidly and then stopped, completely shut down star formation within a few hundred million years of the Big Bang. The shutdown was rapid. The spectroscopic analysis suggested a burst of star formation lasting perhaps 30 to 90 million years, followed by essentially complete quenching. A galaxy that went from forming stars to being dead in a cosmological instant. What could quench a galaxy in 30 to 90 million years? The leading candidate is feedback from a supermassive black hole. If the central black hole accreted rapidly enough and produced enough energy through its radiation and jets, It could heat the galaxy's gas supply to temperatures where it could no longer cool and form stars, essentially cooking the galaxy's star-forming material into an unusable state. This mechanism, AGN feedback quenching, is included in standard models. But the rapidity of the quenching seen in JADE's Gwst Z7-01QU is at the extreme end of what the models produce. The black hole would need to be extraordinarily massive and extraordinarily active to quench a galaxy that quickly. Which brings us back to the overmassive black hole problem. If early galaxies have black holes that are disproportionately massive for their galaxy size, then those massive black holes might be capable of quenching their host galaxies far more rapidly than expected. The findings connect. The massive early galaxies, the overmassive black holes, the rapid early quenching, they are not independent anomalies. They may be different aspects of the same underlying story about how the first galaxies formed and evolved, a story that the standard model captures only approximately. Now let's go even further back. Because some of Webb's most extraordinary findings concern not the first galaxies but the first stars, objects that have never been directly observed, that existed before the first galaxies assembled, and whose properties are known only through inference and simulation. The first stars, sometimes called population 3 stars, were unlike any stars in the present universe. They formed from pristine hydrogen and helium gas, with no heavy elements to influence the cooling of the gas clouds from which they emerged. Without the cooling effects of heavier elements, the gas clouds that formed population 3 stars could not fragment into the small clumps that produce lower mass stars. The first stars were therefore expected to be extraordinarily massive, hundreds to possibly thousands of solar masses. They were hot, blue, and extremely luminous, and they lived for only a few million years before exhausting their fuel and dying in spectacular explosions, hypernovae, that seeded the surrounding gas with the first heavy elements ever to exist in the universe. Population 3 stars have never been directly detected. They formed and died before any telescope had ever looked at the sky, and their individual light has been shifted to wavelengths so long by cosmic expansion that detecting a single population 3 star was considered essentially impossible. Webb has found candidates. In 2023, a team of astronomers analyzing Webb spectroscopy of a galaxy cluster at redshift 6.6, when the universe was about 900 million years old, found a highly magnified arc of light behind the cluster, produced by gravitational lensing. Within that arc, they identified a compact source with spectroscopic properties that are most naturally explained by a very young stellar population containing population 3 stars. The signatures are subtle. Population 3 stars produce a specific pattern of emission lines, particularly a strong helium emission line, that is different from the emission produced by stellar populations enriched with heavy elements. The source identified in the Webb data showed these signatures. This is not a confirmed detection. The team was careful to describe it as a candidate. Other explanations, an unusual compact stellar cluster, an active galactic nucleus with specific spectral properties, cannot be fully ruled out. But if it is confirmed, if Webb has detected the light of population 3 stars, the very first generation of stars to ever exist, it would be one of the most significant astronomical discoveries in history. It would provide the first direct observational constraints on the properties of the first stars, allowing theorists to test their models against actual data rather than inference. The significance extends beyond the stars themselves. Population 3 stars are responsible for the first heavy element enrichment in the universe. Their deaths are the origin of the carbon and oxygen and iron that ultimately made planets and life possible. Understanding them is understanding the beginning of the chain that led to everything. Webb may have seen the first link in that chain. Let's talk about the cosmic reionization epoch, because this is one of the most important periods in cosmic history, and Webb is revealing it in detail that was never previously possible. After recombination at 380,000 years, the universe was filled with neutral hydrogen gas. The electrons had combined with protons into neutral atoms, and the universe became transparent to light. This transparency is why we can see the cosmic microwave background. The light released at recombination can travel to us today without being absorbed. But neutral hydrogen absorbs ultraviolet light very efficiently. A universe full of neutral hydrogen is opaque to the ultraviolet photons produced by the first hot, massive stars. This means that before the first stars formed, and for some time after they formed, while only a relatively small number existed, the universe was opaque to ultraviolet light in a way that it is not today. The epoch of reionization is the period during which the first stars and galaxies produced enough ultraviolet radiation to ionize the surrounding neutral hydrogen, to strip the electrons back off the protons, turning neutral hydrogen back into ionized plasma. Once the hydrogen is ionized, the universe becomes transparent to ultraviolet light again, and the intergalactic medium reaches roughly the state it is in today. Understanding when reionization occurred and how quickly it proceeded is one of the central goals of observational cosmology, because it tells us about the properties and numbers of the first light sources in the universe. The Standard Model predicts a specific history of reionization. It began at around 800 million years after the Big Bang and was largely complete by about 1 billion years. It was a gradual process. Ionized bubbles grew around sources of ultraviolet radiation, merged, and eventually overlapped to produce the fully ionized intergalactic medium of later epochs. Webb is revealing that reionization's timeline and character are more complex than this simple picture suggests. Observations of high-redshift galaxies with Webb are finding, in some cases, that the intergalactic medium around these galaxies is less ionized than expected, that even at times when reionization should be well advanced, patches of neutral hydrogen persist in ways the models did not predict. In other cases, galaxies at early times appear to have produced far more ionizing radiation than expected. Their ultraviolet output is higher than models of their stellar populations would suggest. Both of these findings complicate the standard reionization picture. If the intergalactic medium is patchier and less uniformly ionized than expected, the sources of ionizing radiation may be fewer and more concentrated than assumed. If individual galaxies produce more ionizing radiation than expected, the number of galaxies required to complete reionization may be smaller than the models assumed. The picture of reionization that is emerging from Webb is more complex, more spatially variable, and in some respects harder to model than the smooth, gradual process that the standard framework described. It is, in short, messier than expected, which is increasingly the theme of everything Webb is finding about the early universe. Here is something that deserves careful attention because it is often misrepresented in popular accounts of these discoveries. James Webb is not breaking cosmology. It is not overturning the Big Bang. It is not showing that the Standard Model is wrong in its foundations, that the universe is not 13.8 billion years old, that the cosmic microwave background is not what we think it is, that dark matter and dark energy do not exist. These fundamentals are not being challenged by Webb's findings. What is being challenged is the layer of models built on top of those foundations, the models of how galaxies form within the standard cosmological framework, how quickly dark matter halos assemble, how efficiently gas converts to stars, how rapidly star formation can be quenched, what the first stars were like, how quickly chemical enrichment proceeds. These models, sometimes called semi-analytic models or hydrodynamic simulations of galaxy formation, are not as fundamental as the cosmological framework they sit within. They are built on reasonable physical assumptions, but they involve simplifications, approximations, and parameters that are calibrated to match observations in the nearby, later universe. Extrapolating them to the earliest epochs is always an act of inference. Webb is revealing that those inferences were, in some cases, wrong, or incomplete, or that the early universe operated under conditions sufficiently different from the later universe that the models built on local observations did not capture them correctly. This is not a crisis for cosmology. It is cosmology working exactly as it should, building models, testing them against observations, finding where they fail, and revising them. The revision that Webb is demanding is significant. It is not a small parameter adjustment. It requires rethinking how efficiently the early universe formed stars, how quickly black holes grew, how rapidly chemical enrichment proceeded, and possibly what the conditions of the very early universe were in ways that fed through into the formation of the first structures. This rethinking is happening. Theorists around the world are running new simulations, testing new mechanisms, exploring new frameworks. Some of the new models do better than the old ones at matching what Webb is finding. None of them yet fully explains everything. The map is being redrawn. Let's talk about what the scientific community has proposed as explanations for the aggregate of Webb's surprising findings, because this is where the genuine uncertainty lies and where the most interesting theoretical work is happening. The first category of explanation is modifications to the star formation efficiency in early galaxies. Standard models assume that a certain fraction of the gas in a dark matter halo is converted to stars. This fraction, called the star formation efficiency, is calibrated to match observations of galaxies in the nearby universe. If the early universe had a higher star formation efficiency, if more of the available gas was converted to stars more quickly, then galaxies could grow faster and more massive than standard models predict. What might cause higher early star formation efficiency? Several mechanisms have been proposed. The gas in the early universe may have been more turbulent, leading to more rapid compression and star formation. The cooling of gas in the early universe, in the absence of the feedback processes that regulate star formation in later galaxies, may have proceeded faster. The first generation of very massive stars may have produced more ionizing radiation and mechanical energy, driving gas compression in surrounding regions. These are plausible modifications. Some of them are being incorporated into updated simulations. They can reduce the discrepancy between models and observations, though they do not yet fully resolve it. The second category involves modifications to the initial mass function, the distribution of stellar masses produced by star formation. Standard models assume a specific distribution, the Salpeter or Chabrier initial mass function, in which the number of stars decreases steeply with increasing mass. If the early universe preferentially produced more massive stars, if the initial mass function was more top-heavy, then each unit of gas converted to stars would produce more luminosity and more heavy element enrichment than standard models predict. A top-heavy initial mass function in the early universe is not just an ad hoc proposal. There are theoretical reasons to expect that star formation in metal-poor, high-temperature gas would produce more massive stars than star formation in the cooler, more enriched gas of the later universe. And some observational evidence from nearby metal-poor star-forming regions supports this idea. If the initial mass function was significantly more top-heavy in the early universe, it could explain simultaneously the high luminosities, the rapid chemical enrichment, and the rapid quenching seen in early galaxies. All of these are consequences of having more massive, shorter-lived, more luminous stars. The third category is perhaps the most radical. Some theorists have proposed modifications to the cosmological framework itself, not to the Big Bang or to the fundamental physics, but to the properties of dark matter. Standard dark matter, the cold, weakly interacting, non-self-interacting dark matter of the standard model, predicts a specific distribution of dark matter halo masses in the early universe. If dark matter has slightly different properties, if it is not completely cold, if it has some small but non-zero velocity dispersion, if it interacts with itself or with other particles, the distribution of early halos could be different. Specifically, warm dark matter or fuzzy dark matter, models in which dark matter particles are lighter and therefore move faster, suppressing the formation of the smallest halos, could change the structure of the early universe in ways that affect galaxy formation. The changes required to explain the Webb findings through dark matter modifications are, in most cases, small enough to be consistent with other constraints on dark matter properties. They have not been ruled out, and they represent an intriguing possibility that the early universe's structure was shaped by dark matter properties that are slightly different from the simplest cold dark matter model. None of these explanations have been conclusively confirmed. All of them are being tested. All of them involve real physical mechanisms that could genuinely affect galaxy formation in the early universe. The answer is probably not a single mechanism, but a combination. The early universe was likely more efficient at forming stars, probably had a more top-heavy stellar mass distribution, and the dark matter may have properties slightly different from the minimal cold dark matter model. The combination of these effects, properly modeled, may eventually produce predictions that match what Webb is finding. But that model does not yet exist in complete form. Let's talk about what Webb found that was not about early galaxies at all, but that is equally significant for our understanding of the universe. In 2023, Webb obtained spectroscopic data on the atmospheres of exoplanets, planets orbiting other stars, at a precision that was not previously achievable. The most celebrated of these observations involved a planet called TRAPPIST-1c. The TRAPPIST-1 system, 7 Earth-sized planets orbiting a small red dwarf star 40 light-years away, is one of the most studied planetary systems in astronomy, because several of its planets are in or near the habitable zone and are potential candidates for life. TRAPPIST-1c, the second planet from the star, is too warm to be in the habitable zone. But its proximity to the star and its relatively small size make it a useful test case for studying the atmospheres of rocky planets with Webb. Webb's thermal emission measurements of TRAPPIST-1c placed constraints on its atmosphere that were significant. The data suggested that if TRAPPIST-1c has an atmosphere at all, it is not a thick, Venus-like carbon dioxide atmosphere. A thick atmosphere would retain heat in a way that would show up in Webb's measurement of the planet's thermal emission, and that signature was not clearly detected. This is not a definitive detection of no atmosphere. It is a constraint, but it is the tightest constraint ever placed on the atmosphere of a rocky exoplanet, and it demonstrates that Webb has the capability to characterize the atmospheres of Earth-sized planets in ways that no previous instrument could approach. More significant was Webb's observation of the exoplanet K2-18b, a subneptune-sized planet about 8.6 times Earth's mass, orbiting in the habitable zone of a red dwarf star 120 light-years away. Webb's spectroscopic analysis of K2-18b's atmosphere detected carbon dioxide and methane, both already known from Hubble observations, but also a tentative detection of dimethyl sulfide. Dimethyl sulfide is a molecule that, on Earth, is produced almost exclusively by biological processes, specifically by marine phytoplankton. It is what gives the ocean its characteristic smell when you stand on a beach. It is one of the molecules that has been proposed as a potential biosignature, a chemical sign of life, if detected in an exoplanet's atmosphere. The Webb detection of dimethyl sulfide in K2-18b's atmosphere was described as tentative, not confirmed, requiring further observations to reach the statistical threshold of a secure detection. The scientific community was appropriately cautious. There are abiotic processes that can produce dimethyl sulfide in small quantities, and K2-18b's composition and conditions are sufficiently unusual that a biological interpretation would require extraordinary evidence. But the detection of dimethyl sulfide on K2-18b, even as a tentative signal, demonstrated something extraordinary. Webb can detect potential biosignature molecules in the atmospheres of planets 120 light-years away. The capability exists, the precision is there, and the solar neighborhood contains many red dwarf systems with potentially habitable planets that are accessible to this technique. If life exists elsewhere, if biology is happening in planetary atmospheres within a few hundred light-years of Earth, Webb has demonstrated that it has, in principle, the tools to find it. Now let's step back from the specific findings and talk about what they collectively mean for the way scientists think about the universe. Science progresses in 2 modes. The first mode is normal science, the accumulation of data that confirms and refines existing models, filling in gaps, improving precision, extending coverage. Most science is normal science most of the time. It is valuable and important, and it is what has built our understanding of the universe over the past century. The second mode, rarer, more disruptive, more intellectually uncomfortable, is what the philosopher of science Thomas Kuhn called paradigm shift. The accumulation of anomalies that do not fit the existing framework eventually reaches a point where the framework itself needs to be revised or replaced. This revision is always painful, always contested, and always eventually productive. Are Webb's findings pushing cosmology toward a paradigm shift? The honest answer is we do not know yet. The findings are real. The anomalies are genuine. The standard models of galaxy formation are under serious strain in ways they were not 4 years ago. The theorists are working hard to understand whether the anomalies can be absorbed within a modified version of the existing framework or whether something more fundamental needs to change. Most working cosmologists believe at this stage that the standard cosmological framework, the Big Bang, inflation, dark matter, dark energy, the large-scale structure of the universe, remains fundamentally correct. What Webb is challenging is not the foundation but the superstructure, the models of galaxy formation built on top of the foundation. But a few voices, cautious ones, careful ones, not the cranks but serious researchers, are asking whether some of what Webb is finding might be pointing towards something deeper. Whether the overmassive black holes and the too bright early galaxies and the too rapid quenching and the too organized early structures might collectively be telling us something about the initial conditions of the universe, or about dark matter, or about some physical process in the very early universe that current models do not include. These voices are in the minority, but they are not being dismissed, because Webb's data is real, and real data always wins eventually. Let's talk about what Webb is going to find in the next few years, because the telescope is not done. It is several years into an expected science life of at least 20 years, with fuel reserves that may allow it to operate for longer. The data still coming in will dwarf what has already been analyzed. The Jwst survey, the primary deep survey program that has produced many of the most significant early universe findings, will continue to accumulate data. Each new observing cycle adds more depth, more area, and more spectroscopic confirmation of candidates identified in previous cycles. The Cosmos Webb survey, a wider, shallower program covering a larger area, will provide the statistical sample needed to determine whether the anomalous galaxies found in deep surveys are truly representative or statistical outliers. The Jwst Advanced Deep Extragalactic Survey of Protoclusters, searching for the earliest galaxy clusters, the precursors of the massive clusters that dominate the later universe, will reveal whether the overly massive early galaxies are preferentially found in dense environments, which would have implications for understanding how environment affects the efficiency of early star formation. And the Exoplanet Atmosphere program will continue and expand. More TRAPPIST-1 planets, more nearby habitable zone candidates. The search for biosignatures that began with K2-18b will be refined and extended to more targets. In the next 5 years, if a biosignature is detected at sufficient statistical significance to be considered a genuine discovery, it will be one of the most significant findings in the history of science. Not a confirmation of life that would require much more, but a strong indication, requiring explanation, that something is producing biologically associated molecules in the atmosphere of a world orbiting another star. Webb has made this possible. Here is the thing about all of this that is worth sitting with. Every single one of these findings, the massive early galaxies, the overmassive black holes, the rapid quenching, the chemical enrichment, the early disks, the population 3-star candidate, the potential biosignature, was available in principle before Webb launched. Not available in practice. The observations required the precision and sensitivity of Webb. But the physics was there. The early universe existed. The galaxies existed. The exoplanet atmospheres existed. The molecules were present. We just could not see them. For the entire history of modern astronomy, for the 100 years since we understood that the Milky Way is a galaxy among billions, all of this was out there. The early universe was forming galaxies in ways that the models did not capture. The first stars were burning and dying in hundreds of millions of years. The chemical enrichment was proceeding faster than expected. The exoplanet atmospheres were filled with molecules that instruments on Earth could not detect. All of it was there. We just did not have the eyes to see it. Webb gave us the eyes. And what the universe showed us, the moment we could see clearly enough, was more complex, more rich, more surprising, and more difficult to explain than the models predicted. It is almost always this way. Every time science builds an instrument capable of seeing something it could not see before, the universe shows something unexpected. The radio universe was unexpected. The X-ray universe was unexpected. The infrared universe was unexpected. The gravitational wave universe was unexpected. The universe, at every wavelength, at every scale, at every epoch, keeps finding ways to surprise the people who build the tools to look at it. Webb is the most powerful eye we have ever built, and the universe has met the challenge, as it always does, by showing us things we did not expect to see. Let's come back to Earth, to the night sky above you right now. Somewhere in the constellation Orion, easy to find in the winter sky, the three stars of the belt pointing towards Sirius below and the V-shape of Taurus above. The Orion Nebula is a fuzzy patch of light visible to the naked eye. A stellar nursery, a place where new stars are being born from collapsing gas clouds, radiating infrared light that was invisible before Webb. Webb imaged the Orion Nebula. The images showed, in extraordinary detail, the process of star formation, protostellar jets, planetary debris disks around young stars, the shock waves where stellar winds meet the surrounding gas. A scene of creation that has been happening for millions of years, invisible before Webb, now laid out in extraordinary clarity. In that image, in those jets and disks and shock waves, the same processes are playing out that played out in the early universe, in the first stars, in the galaxies that are confusing theorists with their unexpected size and brightness and chemical richness. The same physics, the same collapse of gas under gravity, the same ignition of nuclear fusion, the same stellar winds and the same eventual supernovae. The universe is consistent. What happened in the early universe with the first stars is happening now, scaled down and refined by billions of years of chemical enrichment in the Orion Nebula 400 light-years away. And Webb can see all of it, from the nearest stellar nurseries to the most distant galaxies in the observable universe. Webb's infrared eyes cover the full range of cosmic history. Every image is a data point. Every spectrum is a constraint on the models. Every surprising finding is an invitation to think more carefully about what we thought we knew. The universe is not finished surprising us. Webb is not finished looking. And the scientists who are reading the data are not finished revising their understanding of how everything came to be. The map is changing. The territory, as always, is stranger than the map. There is something personally significant in all of this that I want to spend some time on before we come to the end. You are alive at a specific moment, not a random moment, a specific one that will not be repeated. The moment when the James Webb Space Telescope is operational and returning data. The moment when the first deep images of the early universe at this resolution and sensitivity are being analyzed. The moment when the first tentative detections of potential biosignatures in exoplanet atmospheres are being obtained and reported. These are not ordinary moments in the history of science. The equivalent moment in the history of astronomy, the moment closest in significance to what is happening now, might be Galileo turning a telescope toward the sky for the first time and seeing moons orbiting Jupiter, craters on the moon, phases of Venus, countless stars in the Milky Way. Observations that shattered a cosmological model that had been in place for 2,000 years and replaced it with one that still underlies our understanding today. Or perhaps Edwin Hubble sitting at the 100-inch telescope at Mount Wilson in 1923, identifying a Cepheid variable star in what was then called the Andromeda Nebula and calculating that it was far too distant to be inside the Milky Way, the observation that proved the existence of other galaxies and expanded the known universe by a factor of billions in one night. Or perhaps Penzias and Wilson in 1964, failing to eliminate a persistent noise in their microwave antenna and eventually understanding that they were detecting the cosmic microwave background, the afterglow of the Big Bang, filling the entire sky, confirmation that the universe had a beginning. These are the moments when the universe shows us something about itself that we did not know before, that changes permanently what we understand about where we are and how we came to be here. We are living in one of those moments, not a minor one, not a refinement, a moment when the most powerful telescope ever built is showing us an early universe that does not match our models, when the picture of how everything began is being revised, in real time, by data that no previous generation of scientists had access to. You are here for this. In the whole history of the universe, in the 13.8 billion years since the Big Bang, through the dark ages and the first stars and the first galaxies and the billions of years of stellar generations that built the elements of life and the planets and the eventual emergence of biology and intelligence. You are here in the specific moment when the intelligence has built an instrument capable of seeing back almost to the beginning and is discovering that the beginning was stranger than expected. That is not a small thing to be present for. The universe is showing us something new, and we are here to see it. Sleep well. For those still listening, As the boundary between waking and sleep continues to dissolve, my biggest goal on this channel is to reach 1,000 subscribers. If you enjoy falling asleep to my videos, please hit that subscribe button. We continue. The images from James Webb are not going away. The massive early galaxies will still be there when the next survey cycle is complete. The overmassive black holes will still be there when the theorists have finished their new simulations. The potential biosignature on K2-18b will be observed again, with longer integration times, with the statistical precision needed to say with confidence whether dimethyl sulfide is really there. The process is slow, careful, disciplined. Science does not rush to conclusions, even when the data is extraordinary. Every claim is checked. Every result is scrutinized by skeptics who look for alternative explanations. Every detection is held to the standard of reproducibility and statistical significance. This is not timidity. It is the method that makes the conclusions trustworthy when they finally arrive. And they will arrive, not all at once, not with the drama of a single announcement that resolves everything, but gradually as more data accumulates, as more spectra are obtained, as more simulations are run and tested against observations, a clearer picture will emerge. The early universe, viewed through Webb's infrared eyes, will eventually be understood. Not perfectly, science never produces perfect understanding, only progressively better approximation. But understood well enough that the anomalies become features, the surprises become predictions, and the map matches the territory at a new level of detail. And at some point, perhaps sooner than anyone expects, or perhaps after years of careful accumulation of evidence, there may be an announcement about K2-18b or another nearby exoplanet that changes the conversation about life in the universe in the way that Galileo's moons of Jupiter changed the conversation about the Earth's place in the cosmos. Not confirmation of intelligence, not contact, but a spectrum, a chemical signature, a pattern of molecules in an atmosphere 120 light-years away that is most naturally explained by biology. If that day comes, and Webb has demonstrated that it is now possible in principle, then the moment we are living in will be understood, in retrospect, as the beginning of the answer to the oldest question. Are we alone? Webb is looking. The data is coming in. Sleep well.